Assalamu alaikum dear students. I am your instructor Muhammad Ishaq for the course Applied Physics of semester spring 2020 in the Department of Computer Science and Software Engineering at Sayyid Case Institute of Technology. Unfortunately, due to the current situation, we could not continue our classes in formal classroom. Rather, we are going to record the lectures and give you the recorded lectures on website, maybe on Google Drive, where you can see those lectures. We will give you time after uploading the lecture. When you go through that lecture, if you have any queries, you can ask those questions. We will set a time slot in which you can ask any question after you go through the last lecture, and we will entertain those queries through WhatsApp. Inshallah, the WhatsApp group is already formed, and I will record those lectures starting from the third week, rather fourth week. Those fourth week lectures would start off revision for you, in which we have started chapter 3, resistance. This chapter is covered from the book Introductory Circuit Analysis by Ballasted. You can consider this stuff from the second book, Fundamental of Physics by Khaled A. Reznik, chapter 26. So let's start today's lecture. Today's lesson contents are introduction to resistance, circular wires, resistance metric units, and temperature effects. This stuff we have already covered. I will give a separate lecture on this topic. Just quickly go through this and arrive at the point where we have last time finished. So this we have already gone through. Resistance of a material or a wire depends upon these four factors: resistivity of material, length, cross-sectional area, and temperature. So if you keep the temperature constant, the resistance will be equal to rho L over A, where rho is the resistivity, L is the length, and A is the cross-sectional area. So this resistivity is material dependent. Maybe material is of copper, silver, gold, and so on. So if material changes, the resistance also changes. So if material is copper or iron, then resistivity would be different. In this case, rho 2 is greater than rho 1. So the resistivity of copper is higher than the resistivity of iron is higher than the resistivity of copper. So resistance would be higher for iron as compared to copper, with other parameters kept constant. Similarly, the longer the length of the conductor, more would be the resistance. If cross-sectional area is higher, then the resistance would be lower. as the resistance is inversely proportional to the cross-sectional area. The smaller the area of the conductor, the more the resistance. So in this case, resistance of second conductor would be higher than the resistance of first conductor. Lastly, if the higher the temperature of a conductor, the more the resistance. Then we talk about the units of resistivity, which are specified in circular mils ohm per feet, where circular mils are the units of the area and feet is the unit of length. So area is usually measured in circular mils. One mil is 1/1000 of inches. So we have last time see the relationship between square mil and circular mil. So 1 square mil is equal to pi/4 circular mils. So resistivity of different material is specified in this table. You can compare the resistivity of different materials with reference to copper. This is an example last time we covered. Okay. These are the factors which affect the selection of a material for conducting wires. Then we have seen the unit of resistance in metric unit system. In metric units, the resistivity of material is specified in ohm centimeter. In this case, copper have resistivity of this much in ohm centimeter and is compared with the semiconductor and insulator. This we have seen last time, wire tables. Wire tables are used to gauge the diameter or capacity of wire, in which we have seen the American wire gauge. These are the codes which are used for different wires. These codes basically signifies the current rating of a particular gauge. For example, for a wire with gauge 1, it can carry a current of around 130 amperes as compared to the gauge 2 wire, which can handle current of 115 amperes. So as the gauge number increases, the capacity of the gauge decreases. There are other standards which are used, in which standard wire gauge and local wire gauges, which are also famous. This is the topic that I would like to cover in more detail: temperature effects in conductors. Then we will see temperature effect in semiconductors and then insulators. So first we start with the temperature effects in conductors. When you increase the temperature of a conducting material, then the resistance of the conductor would start increasing. As you can see from the graph, if I increase the temperature, resistance would be increased. Why this resistance increases? What is the phenomena occurring within the conductor when you increase the temperature? So actually, when you increase the thermal energy, the intensity of random motion of particles within the material increases and made it increasingly difficult for a general drift of electrons in any one direction to be established. So as you know, in a conductor there are a large number of free carriers which move randomly through the conductor, and during this random motion they collide with each other. So students, अगर थर्मल एनर्जी इंक्रीज होगी तो जो रैंडम मोशन की जो इंटेंसिटी है वो भी इंक्रीज करेगी. तो इसकी एग्जांपल आप ये समझ लें कि जैसे आप कॉरिडोर में बहुत सारे लोग जो है वो वहाँ पे खड़े हैं और आपने एक एंड से दूसरे एंड की तरफ मूव करना है और अचानक ही वहाँ पे भगदड़ मच जाती है, जिसका मतलब ये है कि आपकी जो थर्मल एनर्जी अगर इंक्रीज़ करती है लाइट से, तो जो इलेक्ट्रॉन्स हैं वो बहुत तेज़ी से वाइब्रेट करना शुरू कर देंगे या मूव करना शुरू कर देंगे. सेम गोज़ कि आपकी जो कॉरिडोर में जो लोग हैं वो बहुत तेज़ी से मूव करना शुरू कर देंगे. तो देन इट वुड बी वेरी डिफ़िकल्ट फॉर अ पर्सन टू क्रॉस दैट path or go through from one end to the other end of the corridor. So in other words, the resistance would be increased if the random motion of the particle increases. So the result is that for good conductors an increase in temperature will result in an increase in the resistance level. So consequently conductors have a positive temperature coefficient. So positive temperature coefficient means as the temperature increases the resistance also increases. If the materials have negative temperature coefficient, that means the resistance would decrease as the temperature increases. So materials which have the tendency of the reduction in resistance with the increase in temperature are called negative temperature coefficient materials. So like semiconductors are the materials which have negative temperature coefficients, like thermistors and photoconductive cells that we will see later on. In semiconductors, an increase in temperature will result in an increase in the number of free carriers in the material for conduction. So what happens is when you increase the temperature of a semiconductor, the number of electrons would increase. So as the number of electrons increases, the current would start increasing, because the current is the number of electrons passing through a certain area in per unit time. So as number of electrons increases, current would increase, and you know when current increases the resistance would decrease, because resistance is the opposition of the current. So the result is that for semiconductor materials an increase in temperature will result in a decrease in the resistance level. Consequently, semiconductors have negative temperature coefficient. Similar to semiconductors, an increase in temperature will result in a decrease in the resistance of an insulator. So the result is a negative temperature coefficient for insulators as well. So temperature effects. What is inferred absolute temperature? For copper and most other metallic conductors, the resistance increases almost linearly in a straight line relationship with an increase in temperature. So for conductors, their resistance increases linearly in a straight line as temperature increases. So this is a profile of the resistance versus temperature. So if temperature increases, the resistance linearly increases. So this blue curve basically shows the change in resistance as temperature changes. So this curve intersects the x-axis or temperature axis at around minus 273.15 degrees centigrade, which indicates that resistance of copper would be 0 at this temperature. This temperature is the 0 degree Kelvin, which is also called the absolute zero. So at absolute zero, the resistance becomes 0 for a copper. So this curve deviates from the straight line at far end of the temperature on either side. If the temperature goes very low or it goes very high, the curve deviates from the straight line, as you can see. So if you approximate this blue curve with a straight line, you draw a straight line which goes with this curve, so that this intersects the axis at minus 234.5 degrees centigrade, where the resistance is 0. So this temperature is called the inferred absolute zero for copper material. So this straight line is an approximation to this blue curve, just to establish a relationship for the resistance as a function of temperature. So for determining the resistance at any temperature, we can use this straight line approximation. Okay, the temperature of minus 234.5 degrees centigrade is called the inferred absolute temperature for copper. So for different conducting materials, intersection of the straight line approximation will occur at different temperatures. The table is provided here for inferred absolute temperature for different materials. For silver it is minus 243 degrees centigrade, and for copper it is minus 234.5 degrees centigrade, and for other materials it is indicated here. So this temperature basically indicates that for different material, the resistance of that material would be a 0 at this inferred absolute temperature. So for example, if silver is make cooler and cooler, and is अगर आप सिल्वर को बहुत ज़्यादा कूल करेंगे, ठंडा करेंगे, तो ये तकरीबन माइनस 243 डिग्री सेंटीग्रेड के ऊपर जाके इसकी जो रेजिस्टेंस होगी वो ज़ीरो हो जाएगी. So just like in superconductors, in superconductors they have zero resistance, but the temperature would be very low, and at 0 degree Kelvin every conductor have zero resistance, and it becomes a superconductor. So at these temperatures, if you reduce the temperature to this level, these materials becomes superconductor. So we can use this straight line to compute the resistance of any material at any temperature. For example, I can determine the resistance of copper at temperature T2 if I know the resistance of copper at temperature T1. So if I know value of resistance at temperature T1, I can determine the value of resistance at temperature T2. If temperature increase, the resistance would be increased. For conductors, I know the resistance would increase. How much it will increase, that I can compute using this relationship. So how this relationship is established? This relationship is established using this straight line approximation. So if I model this curve with straight line, then from this graph I can say that x over r1 would be equal to y over r2, where x is the distance from this point to T1 and y is the distance from this point to T2. And if this is a straight line, then the ratio of x over r1 and y over r2 would be constant and would be equal. So I can arrive this at this point by using this relationship, x over r1 is equal to y over r2. Just to give you an idea, this is a straight line, and if I pick these 2 points, point number 1 have x-intercept 1 and y-intercept 2, and point number 2 have x-intercept 2 and y-intercept 4. So ratio of 2 to 1 would be equal to 4 to 2. 2 to 1 ratio would be equal to 4 to 2. Or you can have x over y would be equal to x1 over y1 would be equal to x2 over y2, which is still it would be equal. So ratio of these 2 points would remain constant. So that's why I have written that this point is x1 and x1 over r1, and this point is y and y over r2. So x over r1 would be equal to y over r2. So what is x? X is nothing but T1 minus this point, T1 minus 234.15. This is x, this is r1, and this is y. Y is basically, so y would be equal to T2 minus this point, T2 minus 234.15 over R2. So if I simplify this, then T1 plus this over R1 would be equal to T2 plus this over R2. So I can take a mod of this value. This can be anything. It would always be negative. So I would take mod, so this remains positive. So I would end up with this relationship. By using this relationship, I can find the value of resistance at any temperature T2 if my initial temperature is T1 and value of resistance at that temperature is R1. So let's take an example. The derivation can easily be adopted as we have already seen. This is an example. If the resistance of a copper wire at freezing, which is 0 degree centigrade, is 30 ohm, what is its resistance at minus 40 degree centigrade? So T1 is 0 degree and resistance at T1 would be 30 ohm, and I am asked to find out the resistance at T2, which is minus 40 degree. So temperature goes down, so resistance should also decrease. So initially it is 30 ohm, then we can use this formula to compute the resistance. So my temperature T1 is 0 degree and resistance 30 ohm. I want to compute the resistance at minus 40 degrees centigrade, what would be the resistance R2? This is the inferred absolute temperature for copper. So the given material is copper, so I know the inferred absolute zero for copper is minus 234.5 degrees centigrade. Taking the mod, the result would be positive. So from this relationship, if I compute the value of R2, then it would be 24.88 ohms, where at 0 degree it was 30 ohm, it is decreased by around 6 ohm. Another example, if the resistance of an aluminium wire at room temperature is 100 milliohm, room temperature 20 degrees centigrade, measured by a milliohm meter. Milliohm meter is the ohm meter to measure the resistance in milliohms. So at what temperature will its resistance increase to 120 ohm? So initially at 20 degrees centigrade resistance is 100 milliohm. What would be the temperature where the resistance is increased to 120 milliohm? So if I know aluminium have positive temperature coefficient, so initially I can guess that the resistance, as the resistance is increased, so temperature would also be higher than 20 degrees centigrade. So let's see, by using the relationship I can compute the value of temperature T2 where the resistance R2 is 120 ohm. So just by plugging the values for aluminium, the inferred absolute zero is minus 236 degrees centigrade. This T1 is the temperature, initial temperature, which is 20 degrees centigrade, where the resistance was 100 milliohm. Now the resistance is 120 milliohm. Then what would be temperature T2? So of course the temperature would be the higher than the 20 degrees centigrade. So here I will be having a positive sign. So by computing the value of T2 from this relationship, I have arrived at this value, which is 71.2 degrees centigrade. So the resistance goes to 120 ohms at this temperature. Another parameter to quantify the sensitivity of material or a conductor gas temperature is called the temperature coefficient, which is designated as alpha 20. Alpha 20 is the temperature coefficient of resistance. So usually this temperature coefficient is specified for any resistance to indicate the dependence of resistance on temperature. So जो आपका ये अल्फ़ा 20 है, ये एक बेसिकली कांस्टेंट नंबर होगा, और ये कांस्टेंट नंबर सिग्निफाई करेगा कि कोई भी रेजिस्टेंस टेम्परेचर के साथ कितनी इसकी वैल्यू चेंज होगी. तो बेसिकली ये जो आपका अल्फ़ा है, ये उस टेम्परेचर जो आपके रेजिस्टेंस है उसकी सेंसिटिविटी को बेसिकली इंडिकेट करता है. अगर अल्फ़ा की वैल्यू लार्ज है तो इसका मतलब होगा कि जो रेजिस्टेंस है वो टेम्परेचर के साथ बहुत ज़्यादा चेंज होगी. अगर अल्फ़ा की वैल्यू बहुत छोटी होगी तो वो बेसिकली बताएगी कि जो रेजिस्टेंस है वो टेम्परेचर के ऊपर ज़्यादा डिपेंड नहीं कर रही. रेजिस्टेंस टेम्परेचर चेंज करने से उसकी वैल्यू इतनी ज़्यादा चेंज नहीं होगी अगर अल्फ़ा की वैल्यू कम होगी. तो अगर जितनी अल्फ़ा की वैल्यू ज़्यादा होगी उतना टेम्परेचर चेंज के ऊपर रेजिस्टेंस की वेरिएशन ज़्यादा होगी. So how can we use this parameter, temperature coefficient, to compute the value of resistance at different temperatures? So let's see how this parameter is used. So where this alpha 20 is referred as temperature coefficient of resistance at a temperature of 20 degrees centigrade. So this 20 indicates the temperature of 20 degree. The higher the temperature coefficient of resistance of a material, the more sensitive the resistance to changes in temperature. So this is the relationship which can be used to compute the value of resistance at any temperature T1. So R1 is the resistance at temperature T1 and R20 is the resistance at 20 degrees centigrade and alpha is the temperature coefficient at 20 degrees centigrade. So I can compute the value of R1 at any temperature T1 higher or lower than 20 degrees centigrade by just plugging the value of temperature, and then if I know the value of alpha and resistance at 20 degrees centigrade, this relationship from this relationship alpha 20 can be defined like this, where this is delta R by delta T and by R20. Now delta R by delta T is the slope of the curve. So for copper is more sensitive to temperature variation than silver, gold or aluminum, although the difference are quite small. So this table basically indicates the temperature coefficient of different materials. And these are the different materials and this is alpha against each material. You can compare the value of alpha for different materials. Here the copper have temperature coefficient higher than the silver or gold, so the copper is more sensitive to temperature variations than any other material. You can see the constant and have alpha very small value. This indicates that this material have little effect due to temperature. So slope defined by alpha 20 for constant n is so small that the curve is almost horizontal. Since R20 of equation, R1 is this is the resistance of conductor at 20 degrees centigrade and T1 minus 20 is the change in temperature from 20 degrees centigrade. The above equation can be written in the following form as well. So this is delta T and this is the resistance at 20 degrees centigrade, and you know resistance is rho L over A. So this equation can be modified like this. So this is a generic resistance whose value can be computed for any delta T, where delta T is the temperature T1 minus 20 degree. So this provides an equation for resistance in terms of all the controlling parameters. So let me see this in another perspective. So this is the equation. Alpha we have defined as temperature coefficient at 20 degrees centigrade. So change in the resistance, which is defined as dr, is directly proportional to dt. We know for positive temperature coefficient materials resistance varies directly with temperature. Also dr is proportional to the R20. So this can be these two can be related with this equation. dra would be equal to alpha R20 dt. The alpha is the constant of proportionality. So we can integrate this equation from both sides. If we integrate it with r from r20 to r1, and this with respect to time, with respect to temperature, which is integrated from 20 degree to T1. So what would be the value of R1 at T1 if its initial value was R20 at 20 degree centigrade? So if you integrate this equation on both sides, on left hand side you can see integration of constant 1 into dr would be equal to r, and limit of integration of r20 to r1, and it would be equal to these two are constants अल्फा r20, ये दोनों आपके इंटीग्रेशन से बाहर आ जाएंगे. Then integration of 1 dt would be equal to t from 20 to t1. So अगर आप इसमें ये लिमिट्स को पुट करेंगे तो this becomes r minus r20, that would be equal to alpha r20 into t1 minus 20. So after rearranging you will get this equation. So this is another way of describing this. ओके स्टूडेंट्स, जो अल्फ़ा है उसके जो यूनिट्स होते हैं वो हैं ओम पर डिग्री सेंटीग्रेड पर ओम. इसका क्या मतलब है? इसका मतलब यह है कि जो कितने ओहम्स जो रेजिस्टेंस है उसकी वैल्यू चेंज होगी, इंक्रीज़ करेगी या डिक्रीज़ करेगी पर डिग्री सेंटीग्रेड पर ओहम. दैट मीन्स कि फॉर एग्ज़ाम्पल मेरे पास अगर एक रेजिस्टेंस है जिसकी वैल्यू 1 ओम है, तो वो कितने ओहम उसकी वैल्यू बढ़ेगी अगर मैं टेम्परेचर 1 डिग्री इंक्रीज़ करता हूँ. तो इसको ज़रा देखते हैं हम. सो फॉर एग्ज़ाम्पल अगर मेरे पास जो अल्फ़ा है वो है 0.1 ओहम पर डिग्री सेंटीग्रेड पर ओहम. इसका मतलब ये है कि जो अगर मेरे पास अल्फ़ा इस तरह से स्पेसिफाइड है 0.1 ओम पर डिग्री सेंटीग्रेड, तो इसका मतलब होगा कि अगर मेरे पास टेम्परेचर 1 डिग्री सेंटीग्रेड होगा तो उसकी वैल्यू 0.1 ओम होगी, और अगर टेम्परेचर मेरा 10 डिग्री सेंटीग्रेड होगा तो अगर टेम्परेचर इंक्रीज़ करेगा 10 डिग्री सेंटीग्रेड हो जाएगा तो उसकी वैल्यू, चूँकि हर डिग्री के ऊपर उसकी वैल्यू 0.1 ओम इंक्रीज़ करेगी, तो 10 डिग्री इंक्रीज़ करने के बाद उसकी वैल्यू हो जाएगी 0.1 इंटू 10. तो अगर मैं इसको जेनेरिक रखता हूँ तो डेल्टा टी टेम्परेचर अगर होगा तो उसकी वैल्यू 0.1 इंटू डेल्टा टी हो जाएगी. दैट इज़ चेंज इन वैल्यू ऑफ रेजिस्टेंस फॉर 1 ओम. So this is the value of resistance that would be changed, and it is पर ओम. तो 1 ओम के लिए इसकी जो रेजिस्टेंस हो जाएगी वो 0.1 इंटू डेल्टा टी हो जाएगी. सो फॉर 1 ओम इट इज़ दिस मच चेंज्ड, एंड फॉर 100 ओम अगर मेरे पास 100 ओम का रेजिस्टेंस होगा तो उसमें जो चेंज आएगा वो इतना चेंज आ जाएगा, मतलब 0.1 इंटू डेल्टा टी इंटू 100. और जेनेरिक अगर मैं इसको देखूँ तो आर अगर कोई रेजिस्टेंस है तो उसकी जो वैल्यू हो जाएगी वो डेल्टा 0.1 टू डेल्टा टी इंटू आर. सो माई न्यू रेजिस्टेंस वुड बिकम ओल्ड रेजिस्टेंस प्लस द चेंज. सो फॉर एग्ज़ाम्पल मेरे पास अगर कोई रेजिस्टेंस है 100 ओम की, तो उसमें एक डेल्टा आर इंक्रीज होगी रेजिस्टेंस. So I can compute delta R with this relationship. Delta R is equal to 0.1 into delta T into 100. So it would be 100. So R new would be equal to 100 plus 100, which is 200. So after 10 degree centigrade, the new resistance would become equal to 100 ohm with temperature coefficient of 0.1. So this relationship is for alpha 20 can be derived from this relationship that we have already seen. From here R20 is shifted to the left side, so after rearranging from this relationship, R20 can be written as R1 minus R20 over T1 minus T20 over R20. R20 को हम इस साइड पे डिवाइड करते हैं. So this is delta R, this is delta T, and this is R20. So alpha can also be specified by this relationship. Okay. So next time we will see what is part per million per degree centigrade. This is also the temperature coefficient, and sometimes the temperature coefficient of resistance is specified using this quantity, which is part per million per degree centigrade. So thank you for this class. Next time we will move on from this point. Thanks.